I want us to deliberate on just these three basic principles. Sorry, let me see. My mic is working. Three basic principle of assigning, electrons to the various orbitals. Yeah. No, you can't just dive into deeper aspect of chemistry without knowing any of these things. So three basic principles of assigning electron across the various orbitals. Now, the first one we are going to be talking about is what we call, that is number one, the deliberating on Pauli's exclusion principle. Yeah, principle. The second one should be Hund's law. Hund's law of maximum multiplicity, as the number three is Aufbau principle. Yes, you must have all this information, this principle across electron distribution. Yes, in an atom. Yes, you must across electron distribution in an atom. Of course, you see, when we mention or when we made mention of orbitals, that is before we come to this, first of all, understand what orbital, right? Yeah, understand what orbital is all about. Orbital or orbitals. When we talk about orbital, it is simply the region in space where there is what high probability of locating an electron. That is what it means. The region in space where there is what high probability of locating an electron. And of course, you have your SPDF orbital. SPDF orbital, S stand for sharp. Let me put it well. We have the sharp principal diffuse fundamental. We're going to talk about that. SPDF orbital. Now, for electron to go into each of these orbitals, you have to follow these principles. First one, Pauli's exclusion principles. I'm going to quote it. Second one is Hund's law of maximum multiplicity. Third one is what? Aufbau principle. But before we go to the principle of assigning electron to the various orbitals, the basic information you need to have about these orbitals. Yeah, though here we'll talk more on that. So let's just go straight to this. Pauli's exclusion principle. Number one of the principle. Remember, we're talking about three basic principles of assigning electron to the what? Various orbitals. Before we come to this, some of the highlights that we're going to go through before we go to that. So I just want you to pay rapt attention. And if you're here with me, do it to send reaction to the video. We talk about Pauli's exclusion principle. What does it state? He said that no two electrons, that is Pauli's exclusion principle. He said that no two electrons in an atom have the identical set of four quantum numbers. There are four quantum number. Four, we have principal, we have azimuthal, we have magnetic, and we have spin. So no two electrons in an atom have the identical set of four quantum number. That is what Pauli's exclusion principle states. Yes, what is the interpretation of that? Say an electron can or may have same principal quantum number. Of course, that's principal quantum number is in charge of what we call the energy levels of an orbital, same azimuthal quantum number, which determines the the orbital shape, same magnetic quantum number, but not the same spin. Yeah. No two electrons have the identical set of 4 quantum number, and the quantum number by their symbol, this is principal quantum number, this is azimuthal, or otherwise known as subsidiary or secondary or angular momentum quantum number. Now, same magnetic and magnetic and then spin. No two electrons in an atom have the identical set of same 4 quantum number. No two electrons in an atom have the identical set of 4 quantum number. He said an electron may probably have same this, but the spin can never be the same. No, spin is talking about, when we talk about spin quantum number, spin can either be your plus or minus half, which means an electron will face up or it face and down. But they cannot face up at the same time, or this one is not okay, this one is okay, or if you don't want, you can go by this and go by this. That it's either this or this, but you cannot spin electron in same direction, same time. Are you seeing it now? So that is why no two electrons in an atom have the identical set of 4 quantum number. They may have same principal quantum number, which determine the energy levels of an orbital, same azimuthal, which determine the shape, same magnetic, which determine the degeneracy or the subshells in an orbital, but not the same spin. So what brought violation to Pauli's exclusion principle, more or less, you can actually say spin quantum number. Yeah. If you spin electron same way, then there is a violation to that. No two electrons in an atom have the identical set of 4 quantum number. Please feel free, when we are here, do well to keep sending reaction to the video. You can as well share to others, bring them on board, because this information is for all and not just for selected few. So do well to invite others to this. Keep sending reaction to show that we are together in this media space. Please keep sending reaction to the video. I wanted to expand it more. Okay. Keep dropping reaction. In case you have question, do well to drop your question as well. So that is just all about Pauli's exclusion principle. No two electrons in an atom have the identical set of 4 quantum number. So at least that's done and dusted. And of course, the quantum number, I told you that the work of principal quantum number is to determine the energy level. Yeah, energy levels of an electron. While when we talk about azimuthal, we're going to take a topic, just caption quantum number. We're going to talk about quantum number, just those numbers we use to designate electrons. So, but let me just give you a brief overview of that. I say principal quantum number determine the energy levels of an orbital. But when we talk about that is our N, stand for principal quantum number. That is the symbol, principal quantum number. This stands for azimuthal quantum number. It can also be called subsidiary quantum number, or you call it secondary quantum number, or you finally call it angular momentum quantum number. So the work of this quantum number, this azimuthal, is to determine orbital shape. And with that, I want you to understand the value can be L can be equal to 0, L can also be equal to 1, L can be equal to 2, and L can be equal to 3. And at L equal to 0, we are talking about S orbital. Don't forget, I told you that orbital is the region in space where there is what high probability of locating an electron. So that is S orbital, and the shape of S orbital is what? Spherical. It is spherical in shape. That is the geometry of S orbital. So take note of that. Take note of that. The same thing is applicable when we talk about, sorry. Let me see if it is not affecting my, oh God. All right, no issue. Let me check if my this thing is intact. All right, so now at L equal to 1, we are talking about P orbital. P orbital. And P orbital is what? Dumbbell. Dumbbell in shape. But when it is 2, we are talking about d orbital, and d orbital is double dumbbell. Yeah, double dumbbell in shape. As for this, that is f orbital, which is what? Compressed or complicated in shape, meaning complicated, meaning it does not conform to a given geometry or geometric shape. Take note of that. Take note of that. You are going somewhere, sorry. The weather is a little bit challenging, but I'm trying to. That's very I will see you. Okay, now, sorry, now, of course, I just want to explain the remaining concepts, yeah, before we finally bid you bye. So, number two, we have what we call Hund's rule. Hund's rule, though, sorry, though before this Hund's rule, I just mentioned only but no principal quantum number that determine this, no size and energy levels of an orbital, while azimuthal determine the shape. I mentioned the respective shape. The work of magnetic quantum number, or whatever magnetic is, actually depend on azimuthal. That is why the value is from minus L to what? Plus L. I'm going to take quantum number as a case study. That's your attention. So now, what do you need to understand here? I said this one determine the degeneracy. Determine what we call the degeneracy. No, when we talk about degeneracy, it's subshell. Yeah, sub energy levels. So that is what you see here. Why spin is talking about orient that the electron cannot be oriented same way. Yeah, that if one electron is facing up, the other one should face down, but they must not be pointing same direction at the same time. That is all about that. Let's go to number two, which we call Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. What does this say? This one said an electron in or the electron in an atom must first be shared singly before pairing take place. That is what Hund's rule is talking about. The electron must first be shared singly before pairing take place. Oh, it's really challenging. Let me see how to pause